Hey everyone, welcome to this explainer. Okay, let's just dive right in. Today, we're exploring the absolute bedrock of all modern hardware, the resistor. They are the quiet regulators of electronic circuits, sitting silently on literally every printed circuit board, from the simplest kid's toy to the most advanced aerospace technology out there. We're going to unpack exactly how they shape current, set voltages, bias transistors, and ultimately keep all our sensitive components totally safe. Seriously, think about this for a second. What actually keeps a massive electric vehicle engine control unit, or even just that delicate pocket-sized smartphone motherboard, from instantly frying the second power surges through it? Well, unregulated electricity is totally chaotic. Without a passive guardian to step in, the sensitive components inside our devices would blow past their limits, overheat, and fail catastrophically. The elegant answer to this massive problem? The resistor.
So here is our roadmap for today. We're going to start with their role as circuit guardians, dive into the physics and anatomy, decode those tricky engineering data sheets, explore some practical applications, and then wrap up with some real-world troubleshooting.
All right, section 1, the guardian of the circuit. Let's see exactly how these components set the absolute limits for electrical flow. At its core, a current-limiting resistor is simply a fixed resistor placed in series with a device. Now, why is this so critical? Well, because most electronic components have super strict maximum current ratings. Take a typical indicator LED, right? It might only be able to handle about 20 milliamps. Microcontroller input pins, usually way less than that. If we exceed those limits, the device heats up, ages prematurely, or just flat out fails. By strategically adding resistance, we're basically throwing up a protective barrier, safely throttling that current flow way before it can reach and wreck the sensitive nonlinear parts of our board. Moving on to section 2. The physics of resistance. Let's look at how pressure and Ohm's law actually make all of this happen.
To really visualize this, it helps to think of electrical current like water flowing through a garden hose. Voltage is basically that high pressure pushing from the tap. The current, that's the actual water itself. And resistance is literally like your hand physically pinching that hose. The tighter you pinch it, meaning the higher the resistance, the less water can actually get through. And that brings us to the absolute golden rule of electronics, Ohm's law. Voltage equals current multiplied by resistance. This direct mathematical relationship is exactly what makes resistors so perfectly predictable and indispensable in circuit analysis. If you know your voltage and you know the absolute maximum current your component can survive, well, Ohm's law tells you exactly how much resistance you need to drop in to keep the whole system perfectly balanced. But, you know, there's a catch here, and it brilliantly illustrates a major real-world engineering challenge: power dissipation. See, when current flows through a resistor, that opposed energy doesn't just magically vanish. No, it converts directly into heat. Using the formula power equals current squared times resistance, we can actually calculate this. So if you're dropping 5 volts across a resistor carrying 20 milliamps for an LED, that little guy is generating 0.1 watts of heat. It has to safely absorb and dissipate that heat, otherwise, it's literally going to burn out right there on your board.
All right, section 3, anatomy of a resistor. Let's peel back the layers and see what's actually inside that tiny black speck. Because engineers don't just grab, any random resistor. They select a very specific technology based on needs. Take carbon composition resistors, for example. They use blended carbon particles. They're older, sure, but they are incredibly tolerant to sudden, massive power surges. Then you have metal film resistors, which deposit a super thin metal layer on a ceramic core. That gives you fantastic precision and really low noise, absolutely perfect for delicate sensor interfaces. And wire wound resistors? They literally wrap resistive wire right around an insulating core, so they can handle massive amounts of power and heat without even breaking a sweat.
You can really see this stark difference in construction right here. On the left, we've got a thick film chip resistor, basically the daily workhorse of modern surface mount tech. You can actually see the dark resistive layer printed flat right onto the substrate. Next to it is a Melf cylindrical resistor. For this one, a conducting film is deposited onto a glass or ceramic core, and then, this is incredibly cool, the exact resistance is fine-tuned by cutting a tiny helical groove straight through that metal film.
Now check out this cutaway of a housed wire-wound resistor. See those physical metal wire coils wrapped tightly around the internal core? That unique, rugged construction is exactly what allows it to handle those extreme power loads we were just talking about. I mean, it's built like an absolute tank. That makes it ideal for incredibly harsh environments like motor drives or high-end power supplies, where a tiny surface mount chip would just instantly vaporize.
Which brings us to section 4, decoding the data sheet. Let's talk about how senior engineers actually hunt down the perfect part for the job. So, the most crucial thing to remember here is that a resistor's value isn't static. It actually changes. Senior engineers heavily scrutinize these 4 specs. Power rating ensures the thing won't melt. Tolerance tells you the manufacturing variance, like a 10K ohm resistor with a 5% tolerance could actually be anywhere from 9.5K to 10.5K out of the box. But really look at TCR and VCR. Real resistors physically change their value as they heat up or as voltage spikes. If you're designing a rock-solid engine control unit that has to survive inside a blazing hot car engine bay, yeah, selecting a resistor with a low temperature coefficient of resistance is absolutely non-negotiable if you want the circuit to remain stable. And you can see exactly why that matters right here. Notice how the allowable power drops off a literal cliff on this derating curve once the ambient temp gets too hot? This is exactly why best practice dictates that a senior engineer will always select a resistor rated for at least twice their calculated power dissipation. You desperately need that massive safety margin, so when the ambient temp inevitably spikes, your resistor doesn't just fail under the load. All right, section 5, practical circuit applications. Let's see how these components are actually implemented out in the real world as dividers and pull-ups. So in digital circuits, think I2C data communication lines, engineers use pull-up resistors to establish perfectly clear logic levels. But it is always a game of trade-offs. If you use a high-resistance pull-up, let's say 10K ohms, you save a ton of precious battery power. But the voltage rises a lot slower because of the natural capacitance in the wires. It essentially acts like a low-pass filter and bogs down your communication speed. On the flip side, a low-resistance pull-up charges the line lightning fast, which is great for high-speed data, but it's going to burn significantly more power every single time a signal drops low. And what about high-precision analog circuits, things like integrated resistive voltage dividers? Well, here, the physical layout on the printed circuit board is honestly just as critical as the part itself. Designers have to follow some incredibly strict rules, aligning the matched elements perfectly side by side, maintaining exactly equal spacing, and orienting the board perfectly orthogonal to the factory printing direction. Doing all this minimizes spatial variations and makes sure the voltage ratio stays rock solid even against crazy temperature and voltage swings. Finally, section 6, real-world troubleshooting. Because when things inevitably break, how do technicians actually find the fault? Let's say you're a technician tasked with diagnosing a completely dead mobile motherboard. You don't just start guessing, right? You follow a strict 4-step diagnostic sequence. Step 1, slip the board right under a microscope and visually hunt for physically burned or cracked resistors. Step 2, analyze the board layout to properly isolate the power sections from the network sections. Step 3, carefully match the physical components on the board back to the engineering schematic. And Step 4, bring out the multimeter and physically probe the suspect component. When they're testing, technicians rely heavily on 3 specific multimeter modes. Continuity mode basically beeps to tell you if the electrical path is unbroken. Voltage mode verifies that the resistor is providing the exact pressure drop we originally calculated with Ohm's law. And diode mode helps confirm the overall health of the nearby semiconductors. If a tiny SMD resistor, maybe one stamped with 102 for 1,000 ohms, is the thing causing a voltage imbalance, using these multimeter modes is exactly how you expose where the current is failing to flow. Which really leaves us with this final thought. Resistors aren't just, passive bits of carbon and metal. They are the highly active protectors of literally every digital experience we rely on. So, the next time a nasty power surge hits and your wildly expensive device miraculously survives without frying, will you recognize the quiet guardian that took the hit for you? Thanks so much for joining me on this explainer, and definitely keep questioning how the world around you is wired.